We're going to be looking today and tomorrow at what's called radioactive decay. There are three main types of radioactive decay, and I say main types because there are other types of radioactive decay. The three we're going to be talking about are alpha decay, beta decay, and gamma decay. And if all goes according to plan, we will cover alpha and beta today, and then tomorrow we will be looking at gamma decay as well as positron decay and something called electron capture. Along the way, we're going to be doing calculations using delta E equals delta MC squared. In 1895, right around the time electrons were discovered and X-rays were discovered, Henri Becquerel, a French physicist, discovered what I refer to as natural radioactivity, because very often this stuff is called radiation. And we had a whole unit on electromagnetic radiation. So this is radiation, but it's natural radiation. And you will see in a second that there is a little bit of overlap between electromagnetic radiation and what we're calling radioactivity. Radioactivity is nuclear in nature. The word nuclear has as its root word nucleus, or nucleus has as its root word nuclear, or maybe they both share a root word, I don't know. But they have to do with the nucleus. So this radiation that Becquerel discovered, alpha radiation, beta radiation, and gamma radiation, is naturally occurring and it originates within the nucleus. That's why it's called nuclear physics. We use the symbol alpha for alpha radiation, beta for beta radiation, and that's a gamma. And when I write a gamma, I will probably write it this way, and it's where we get the letter G from in our alphabet. It's a Greek letter gamma, and it's morphed over time to G. So I will either write it like that, which almost looks like a G. Sometimes I'll just put a little tiny dot on it. But the font that typically is on exams is that weird Y-looking thing, okay? You can't see this radiation, so you need a way to detect it. And our job here today is not to talk about how Becquerel detected it. But if you take a radioactive source, something that Becquerel knows emits naturally alpha radiation, beta radiation, and gamma radiation, and you expose it to a magnetic field, he discovered something. He discovered that the beta radiation is deflected, and by the way, it's deflected in quite an extreme arc compared to the alpha radiation, and the beta radiation is deflected in the opposite direction as the alpha radiation, which tells you that the alpha radiation and beta radiation are oppositely charged. And the fact that the gamma radiation moves through this magnetic field, and I don't know, can you help me out? Did I label that magnetic field there? Is there a B there somewhere that says magnetic field? There isn't, eh? You can add that if you want, or you can just write magnetic field, or you don't have to add anything, but it's a magnetic field. And the magnetic field is symbolized by those dots, which we know from way back in Unit 2 means out. If the particles are streaming to your right through a magnetic field that is out, then that means anything that's deflected towards the top of the page is negative out of the back of your hand. Anything that's not deflected is neutral, anything that's deflected out of the palm of your hand is positive, and anything that's deflected out of the back of your hand is negative. The conclusion that Becquerel draws right away is that alpha radiation and beta radiation consists of particles with mass. Because, and there might be deep in the quantum world some kind of exception to this, but because only things with mass can carry charge. And that might change later depending on our conversation. Whereas the gamma radiation does not have a charge. Now, just because the gamma radiation has no charge doesn't mean it doesn't have mass. It might or it might not. Okay? Turns out it doesn't. Okay? So what is alpha radiation? These alpha particles that we've been talking about, it turns out that's what alpha radiation is. Okay? But alpha radiation consists of positive particles, beta radiation consists of negative particles, gamma radiation carries no charge. He was able to determine that all of these forms of radiation are ionizing forms of radiation. What does that mean? It means that they have the ability to ionize electrons from atoms, which means if they encounter you, they ionize your DNA and they can cause cancer. So these are cancer-causing forms of radiation. So what are these things? Now, everything is typed out on your handout, but I feel the need to just go through these step by step. It turns out that alpha radiations are alpha particles. Okay, so we've been doing all this work with alpha particles from, I wouldn't say day one, but for a very long time we've been working with alpha particles. They are important particles because they are naturally created through certain nuclear processes called alpha decay. Protons are important, electrons are important, alpha particles are important, neutrons are important. That's why we have those four, quote, particles on your formula sheet. You should know, based on yesterday's work, that an alpha particle is a helium-4 nucleus. So in fact, an alpha particle is not a single particle. It's four particles put together. It turns out that beta radiation consists of electrons, which we're going to get to this explanation today, but that's a puzzling aspect to what we're talking about here, because beta radiation comes from the nucleus. And in the nucleus are protons and neutrons and no electrons. So some process is happening inside of the nucleus somehow to produce electrons. These electrons that stream out of something that's decaying, that emits beta radiation, these electrons are not the electrons that are in orbit around the nucleus. They're different electrons. And gamma radiation, and this is the overlap I was talking about, are gamma ray photons. So of all the forms of electromagnetic radiation, radio waves, microwaves, radar, infrared, visible light, ultraviolet, X-ray, gamma rays, the only one in that list that we're talking about today is gamma radiation. So gamma radiation should and can be thought of as a form of electromagnetic radiation, but it can also be thought of as a form of radioactivity or natural radiation. Now, penetrability. Well, I have a Geiger counter here. And it's quite quiet, but you can hear some ticking, and it has nothing to do with the radioactive material I have on this display. If I were to pick this up and move it over here, it's still going to tick every now and then. Right there. And each of those ticks represents either an alpha particle, a beta particle, or a gamma ray photon activating the sensor inside of this Geiger tube. If I were to go outside and point this at the sun, it would start ticking a little more regularly because the sun is emitting different forms of radiation. So I have different sources of radiation. I have alpha radiation. So I'm going to put this on here. So there's alpha radiation coming off of there. If I hold it like this, there's a whole stream of alpha radiation hitting my head. The levels and the energies involved in these samples are low enough that even if I was exposed to this twice a year, because I teach physics 30 usually twice a year, for my whole career, I'm going to be okay. Okay? So your exposure to this is minimal. But let's talk about the penetrability. Because if I take a single sheet of paper and put it in between the source and the Geiger counter, I'm back down to that, what we call background radiation. There might be the odd stray alpha particle that manages to tunnel its way through the paper. But alpha radiation is the weakling in terms of penetrability. It's very easy to block alpha radiation. can be stopped by a couple of sheets of paper. And when I put this paper in here, and you still might hear a few ticks, if I just put a couple of sheets of paper, there is no doubt now that anything that's making the Geiger counter tick is an alpha particle, is a beta particle or a gamma particle, photon, from somewhere else. Okay? I'm going to put on here now beta. And I have this up here so that I can tell which color is which, because for some reason, see how this says beta on it? For some reason now the manufacturers don't stamp that on there. So every time we get a new source, it's just, you're expected to know green is beta. If I take a beta source and put it on here, now it might not be ticking as much as the alpha, or it might tick more. That's not the point. I'm going to turn this down a bit. Don't worry about why. You don't notice the difference, but it's reacting differently. If I were to take that same couple of sheets of paper and put it in here, there's no change. And what that means is that beta radiation is able to penetrate paper. But if I'll take a thin sheet of aluminum that's maybe a millimeter thick, still no change. If I take 2, not much of a change. 3, I don't know if you can tell, but the more sheets I add, the lower it's going. And we don't have time for this, but there's a needle on here. And that's why I turned it down so I can see the needle. Well, every time I put more aluminum in there, the needle is deflected less. So we're now at maybe 1/4 of a centimeter. If I were to use about 1/2 centimeter of aluminum, we're almost absorbing all of the radiation. So how much aluminum is required to block that radiation? Well, this is about 1 centimeter, and if I put 1 centimeter in here, I'm going to have to move this back a bit. Pretty much stopping it. So you need about, this is just a benchmark. This is not a perfect mathematical prediction. It depends as well on the energy of the beta particles. This beta source is strontium-90, which is naturally emitting beta particles, electrons somehow. There are other beta sources out there, and they might emit particles with more energy or with less. I'm going to go now to gamma, and this is, what are we looking at here? Cobalt-60. Now it's not ticking as rapidly, but that's only because there's not as much cobalt-60 material in this sample. If you, I can't really see on here, can you see kind of a dark spot here? That's embedded in the plastic, the cobalt-60. Can you see kind of a dark spottiness here? That's the strontium-90. Do you see this silvery disc? That's the polonium-210. It's not inside of the plastic. Does anybody want to venture a guess as to why the polonium-210 is not inside of the plastic?
It gets stopped. It would be stopped.
It would be stopped. I couldn't demonstrate anything to you if it was inside of the plastic. I would just put it here and say, see, it's not ticking, so the plastic is stopping it. There could be breadcrumbs in there. You wouldn't know the difference. So this is why this one is directly exposed. So now I'm going to go back to the gamma, and I'm going to actually move the gamma further away because I'm going to need some room here. So the gamma is ticking about 1.5 centimeters of paper, no change. About 1 centimeter of aluminum, no change. Lead is a toxic metal. It's called a heavy metal, not, that headbanger kind of heavy metal. And if you get it in your system, it can get in your blood and cause problems. So I've got this taped up, and I'm not touching the lead directly. It is going down a bit, but not a lot. I think I have, I'll just wash my hands afterwards, a fair amount of lead. I don't know if I can fit it in that space. Like, lead's very dense. Lead is a really, really heavy material, and it's still not enough to stop all of the gamma radiation. So what that means is that gamma radiation has the highest penetrability of these three. Now, there's other forms of radiation, but you're expected to know that that is the order of penetrability. And now we have to talk about the hazards. And there's a huge misconception out there, not just in the public, but in the education system, that people think that because the gamma radiation has the highest penetrability, that it's the most dangerous. And to some degree, that is true. I would not want to be exposed to a high blast of gamma radiation. But it turns out that alpha radiation, I don't want to, well, I guess you don't have to write it down, it's already there. Alpha radiation is the most dangerous to you. It can cause the most damage to you. And the reason for that is alpha particles are very, very large. If alpha radiation can be stopped by paper, then it can be stopped by my skin. Would you agree? It never gets inside of me. But what happens when these particles are stopped is they lose their energy. So every time an alpha particle is stopped by my skin, I'm absorbing the energy somehow. And how is that absorbed? Ionization of DNA. Gamma ray photons go right through me. They do. They go right through me. Now, they do some damage on the way. I'm going to get the gamma going again. Put my hand in here. Well, they're going right through me. And they are on the way colliding with ions or atoms and molecules and doing some ionization, doing some damage. But because these are moving so fast, literally at the speed of light for gamma, there are very few collisions that happen as they pass through. It would be like, speaking of the movie Die Hard, I believe there's a scene in the movie Die Hard, I could be thinking of the movie Speed, it doesn't matter, where a bus is out of control and goes down Fifth Avenue in New York, which is loaded with cars, and it hits every car and slowing down a bit, slowing down a bit, slowing down a bit, slowing down a bit, and it damages lots of vehicles. Well, in the same movie, if somebody fired a bullet down Fifth Avenue, it might go through a couple of windshields. It doesn't stop, it just keeps going, losing a bit of its energy along the way, ionizing a few atoms along the way. You understand this is an analogy, right? So this is particularly true if it's ingested. So radium-226, which is what the play that was just completed in our school, Radium Girls, was about, radium-226 is an alpha emitter. And if you're not familiar with Radium Girls, it's a historical play. And I still have a watch from the 70s with the radium dial on it. They were still manufacturing them in the 70s. And then they got rid of it. It's perfectly safe unless you get it in your body. So if I inhaled something, I don't inhale an alpha particle. I inhale a piece of polonium-210, little particle of polonium-210 that's floating by, and I go, and it goes into my lung. And it goes into my lung and it gets caught in the cilia of the lining of my lung, then that is there for a long time. And every second of every day of my life, alpha particles are coming out, being absorbed by that part of the lung, causing damage. So in the play, women were in a factory and they would paint the radium on the dials of a watch so that it would glow in the dark, because this stuff glows in the dark. Not this stuff, but radium does. Why? We can get into that later maybe. But when you paint something with a brush, like a foxtail brush or something, it's very fine work and you want a point on the brush. So you could dip it in water and then, clean it off and get a point on it. But the people in the factory didn't want them wasting uranium. So they used their tongue. Which meant it got on their tongue, they swallowed, it went in their body, and it causes cancer. So in that regard, alpha radiation can be the most dangerous. On the other end of the things, in high doses, gamma radiation is fatal. Like you've heard of Chernobyl, I think. Nuclear meltdown in Chernobyl, Ukraine. Anybody who was exposed to that original blast of gamma radiation was dead within hours, maybe minutes, depending on how much radiation they got. The energy is so intense, forget about ionizing your DNA, it fries all of your tissue inside. It's like being blasted with a microwave. And you go into organ failure, multiple organ failure. Beta radiation is kind of in the middle. I don't think you need to know the details here, but I do think you need to know that if ingested alpha radiation, the source for alpha radiation can really be a problem. Does anybody have any comments or questions regarding that? Go ahead, Armand.
What does the time stand for example, in beta? It said 2028 years.
Well, we're going to talk about that more in the coming days. There's a time given here. And I will tell you, those of you that are in Math 30 now or have taken it, that the time is a half-life. Okay? So the half-life of this strontium-90 is 28.8 years. And what that means is 28.8 years from now, we will still have half of whatever we have now. The half-life of the typical gamma source that we use in high school anyway is 5.27 years. What is the half-life of the polonium? 138 days, which means every 138 days it's cut in half. Now I have a whole bunch, if I can open it, I taped it shut. I have a whole bunch of alpha sources. I got one in here that says 1998 on it. Well, there's nothing left in any of these. So about every year or two, we need to buy another one of these alpha sources, and it turns out you can't just buy the alpha, you have to buy the alpha, beta, and gamma. So I've got a whole boatload of gamma and beta as well, because every time we order an alpha, we get another beta and gamma. So they are called half-lives. And those of you in Math 30-1 know what that means. Any other questions before we move on? Okay, briefly here, I have in here, and it's safe to handle, I'd have to wash my hands afterwards. I have in here, it just looks like a little rock. It's an actual piece of uranium ore. So there is natural radiation, and all of these are again at safe levels. So that's uranium ore. It's uranium. Contains some other isotopes. If I try to stop this with paper, does it go down a bit? It might just be going down because I'm blocking the speaker. I don't know. A lot of alpha radiation, right? But it doesn't stop 100%, does it? So that means there's alpha radiation in here. Now, is that remaining radiation beta or gamma? I don't know. If it's stopped by the aluminum, it's beta. I would say it's beta and gamma. I think there's less now than there was with the paper, but it's still not blocked 100%. Finally, the thing you need to understand is when the uranium, I'll pick on the uranium emits an alpha particle, it turns into something else which might be radioactive and then emit another particle. All right, we're going to move on now and talk about the details of decay equations. So there are conservation laws that are always true without exception during nuclear changes. Conservation of mass is not one of them. Conservation of energy is not one of them. Okay? Energy is never conserved in a nuclear change, and neither is mass, because in a nuclear change, mass turns to energy, or energy turns to mass. But momentum is always conserved, and you are going to encounter problems sooner or later in this unit where you have to apply the law of conservation of momentum. If I told you I held a rifle and I fired a bullet at a target and the bullet left with a particular speed, and you knew the mass of everything, could you find the recoil speed of the rifle? Well, then you can find the recoil speed of a nucleus when it spits out an alpha particle, because it's the same principle. Momentum is conserved. Mass energy is conserved, and I don't want to get into a detour here or a derail, but as I said, mass is not conserved, energy is not conserved, but when you look at all of the mass and energy together in something we call mass energy, it is conserved. The two most important things for today are charge and number of nucleons. And if you look at your formula sheet under the physics principle section, you will see a physics principle called conservation of charge. I want to say it's number 7. I'm right. You will also see a physics principle called conservation of nucleons. Whenever you know how in chemistry you balance a chemical reaction? In nuclear physics, whenever you balance a nuclear reaction, you're using conservation of charge and conservation of nucleons. So let's see how this goes. What happens during alpha decay? Well, alpha decay involves spitting out of the nucleus an alpha particle, 2 protons and 2 neutrons. For whatever reason, and we can't ask why all the time, for whatever reason, polonium-210, which has, where's polonium? 84 protons, and whatever 210 minus 84 neutrons is, 126. For whatever reason, those 84 protons and the 126 neutrons are an unstable arrangement. And it's much more stable if they fired out 2 of each. And that's what happens, but it comes out in the form of an alpha particle. So it happens because the new number and arrangement of nucleons is more stable. Talked a little bit about this yesterday. The reason why things happen in our world is because they become more stable. The reason why hydrogen and oxygen gas react to produce water on their own is because water is more stable than hydrogen and oxygen. The reason why that barn that you pass every summer on the way to the cabin becomes more and more and more and more crumbled over the years is because it's more stable in that arrangement. Things decay naturally. During alpha decay, there is a decrease in mass. We're going to talk more about that. The symbol for an alpha particle we talked about yesterday is this. So I've given us, I think, what's needed to write the decay equation for radium-226, which happens to be the radioactive material they used to paint on watch dials. We have to look up radium, and be careful because there's radon and radium, and they're similar, and they're maybe even very close on the periodic table. So here is radium right here, atomic number 88. So we start off by writing the symbol for radium. We put 226 here, and we put 88 here because radium is atomic number 88. This is just like chemistry. This is what we have before. What do we have after? Well, we have an alpha particle after. And what else do we have? Well, what does the top number represent in isotope notation? Who can tell me what the top number represents? Alex?
Both the neutrons and the protons.
There's a word collectively for neutrons and protons. Nucleons. So nucleons are conserved. Which physics principle is that, by the way? 8? 8? Okay. Not that that's important, I just wanted to know. So if we have 226 nucleons before, we must have 226 after. There are 4 nucleons in the alpha particle, which means we need another 222. Now, what is the bottom number? Well, the bottom number is protons, but I'm going to tell you something right now which might be a bit of a shock to you. Protons are not always conserved. Okay, we'll learn why in a few minutes. What is always conserved is charge. And 88 protons means a charge of positive 88 elementary charges. I want you to think of the bottom number not as particles but as charge. You will see why that becomes very important in a few minutes. And that means I have to have 88 elementary charges that are positive before and 88 after, which makes this 86. Now, I admit you could just think protons, but that's going to let you down in a few minutes. And then we can look up here and see what 86 is, and it is radon. Well, I say look up here because I'm looking at my hanging periodic table. You're looking at your periodic table, which you really ought to have in front of you in case you don't. That's it. Done. Briefly, before we move on. Do you agree that that alpha particle is spit out of the nucleus? It has energy. There's energy released in this change. Where does the energy come from? It comes from the fact that if you find the mass of the radium and you compare it to the mass of these two products, you're going to have less mass afterwards. Mass has been obliterated from the existence of the universe and replaced with energy. Mass has been converted to energy. And that's what the second question is asking us. How much energy is released? Well, we're going to be using this idea that the change in energy is equal to the change in mass times the speed of light squared. It's not binding energy. Sometimes you will see, and it kind of drives me a little nuts, sometimes you will see people call the discrepancy between these two masses that we're going to find the mass defect. I guess you can. But what we want to do here is find the mass of the radium-226. I want you to calculate this in a second. And I want you to as well calculate the mass of the radon-222 plus the alpha particle. And it's okay to work in atomic mass units here. Okay, well, the mass of the radium-226 is 226.025410 atomic mass units. We don't need to calculate anything. The mass of the radon and the helium I better use my calculator. The mass of the radon-222 and the helium nucleus, which is an alpha particle, is 222.017578 plus 4.002603. Double check everything, 017578. I think it looks okay. Is 226.020181 atomic mass units, which is a little bit smaller than the mass we started off with. Do not try to connect this with binding energy and mass defect just yet. Okay? That's for another day. That's for next week, maybe. Maybe. The bottom line is we have a change in mass that's negative. If you take the final mass minus the initial mass, which is how you always find delta of anything, you're going to get a negative number. So I'm going to take the final mass, which is on my calculator, and subtract the initial mass of 226.025410, and get this number of atomic mass units, which you can decide to write down or not, because I need to convert it to kilograms to use my E equals mc squared formula to find the energy. This question was about the energy. So this is the change in the mass. It's negative. If I multiply that by 1.66 times 10 to the negative 27, because that's how many kilograms there are per atomic mass unit, that's from yesterday. This is the change in the mass in kilograms. So this is delta M in atomic mass units. This is delta M in kilograms. So to find the change in the energy, you take the change in the mass times the speed of light squared. By the way, I'm being very clinical about this final minus initial thing for a reason that I'm going to draw your attention to in a second. So I multiply by the speed of light squared. And I get this many joules for my delta E. My delta E is negative 7.81 times 10 to the negative 13 joules, which is, if you want to convert it to electron volts, it's going to be about 4 million electron volts would be my guess. It's a lot of energy. And you know, we're not going to spend class time doing all of the units. If you had a question that wanted to know in electron volts, you do the conversion. But I want to draw your attention to something here, and this is just to help out some of you who are taking chemistry right now. So who's taking Chem 30 right now? Okay, you understand in chemistry you don't use E, you use H, right? What does a negative delta H mean? Exothermic. Well, this is a natural process. It's exothermic. This is all coming together. Things you're learning in chemistry about energy still are applicable here. It's just that the energies here are huge compared to kilojoules. This is less than a kilojoule, right? But this is for one nucleus. A mole of radium would release this much times 6.02 times 10 to the 23. A mole, 6.02 times 10 to the 23 atoms. It'd be a large amount of energy. Okay. All right. Why is the mass of the products less? Because it's exothermic, also known as natural. I don't care whether it's chemical, phase change, nuclear, something that happens on its own will be exothermic. Okay? Means a negative delta E, which means a negative delta M. I don't think we need to bury ourselves in an avalanche of words here. If you want to release energy, you have to lose energy. Nuclear changes involve the production of that energy that's kicked out of the system by removing mass somehow. And When I say it removes mass, I'm not talking about the alpha particle. There's less mass afterwards. Any questions with that first example? Okay, let's talk about beta decay. So beta particles are electrons. How are electrons released from the nucleus? Well, it turns out a neutron is not an elementary particle. And I'm going to say it has parts to it, and then later on in the unit I'll say that's maybe a bad word. But a neutron has parts within it. It's not stable. And every now and then, a neutron changes into 3 particles. Why? Because of the weak nuclear force, which is acting deep, deep, deep inside the nucleus. One of the particles is a proton, one of the particles is an electron, and the third is called an antineutrino. So this is what happens. The symbol for a neutrino, it looks like a V with its hair being blown back in the wind. An antineutrino has a line over it, and there is no charge on a neutrino. It's the weak nuclear force that does this. And you know, as far as it goes, that's all you need to know about the weak nuclear force right now. It's responsible for beta decay. The electron is ejected out of the nucleus, I like to say, because it's not welcome there. What's welcome in the nucleus? Protons and neutrons. So the electron is kicked out. The antineutrino is kicked out as well. So it turns out a neutron is not an elementary particle. So this is the symbol. Let's talk for a minute about this. For a beta particle, also known as an electron. There's nothing wrong with writing that. So what is the top number? 0. That means that there are no nucleons in an electron. What is the bottom number? Well, it's not protons, because we've already established there's no nucleons. The bottom number is charge. And you will get used to this. So let's write the decay equation for the beta decay of thorium-234. So we got to find thorium up there. Well, on your periodic table. We need to know what thorium is. I want to say it's number 90. It is 90. So thorium-234, the symbol for thorium is TH, and it's 90. And this particular nucleus of thorium, there's a gazillion of them floating around inside of a lump of thorium-234. This particular nucleus gets the shakes and spits out a beta particle. It decays. Other ones don't. I mean, do you agree that if I turn on the Geiger counter again, it's still ticking? Well, that means that the uranium that was decaying didn't all decay at once. It's still decaying now. If I come back next year, there's still more that didn't decay. So it isn't everything happening at once. This one decides for whatever reason to decay, and what does it spit out? A beta particle, an antineutrino. How many nucleons in an antineutrino? None. Okay, I haven't really told you what it is yet. Okay, what's the charge on an antineutrino? It turns out it has no charge. Before I finish this, some of you might be wondering, why is this particle here? And the answer is that when physicists study the beta decay of thorium-234, they detect the beta particle, they detect whatever's going to be left over, but momentum isn't conserved when they look at all of those pieces. So someone had the bright idea of saying, you know what, maybe there's another particle. And that accounts for the conservation of momentum. And they went looking for it. Sure enough, they found it. It's a massless, chargeless particle. What's left has no mass, has no charge. There are particles out there with no mass and no charge. They have energy. Anyway, what do we have left? Well, the top number has to be 234. And the bottom number has to be a number that conserves charge. We have a positive 90 of charge here on the left, and we have negative 1 on the right, which means we need 91 here. Because the 91 plus the negative 1 will give you the 90. So we go hunting for number 91, and number 91 is protactinium. I think is that what it's called? Protactinium? Yep. It says describe the decay. So any questions with getting those products? By the way, the thorium is called the parent nucleus, and the protactinium is often referred to as the daughter nucleus. So what about the net change? Well, the fact of the matter is, forgetting about charge, this is 90 protons, and you can do the subtraction for me and confirm that it's 143 neutrons. This changes into a beta particle, and I want you to notice that I wrote a proton just as P plus. So I'm going to write a beta particle as B negative 1. I could put a 1 here if I wanted to. Plus we get an antineutrino which has no charge. Plus we get 91 protons and 140. Did I subtract wrong over here? You guys, you said that was right. I'm going to blame you. It's 144. Thank you. 144 neutrons. That's better. Over here we have 143 neutrons. So just those of you in chemistry, you talk about net ionic reactions, right? If you start off with a beaker on the left and you still have a beaker on the right, that's not changing. Well, what changed is one of these neutrons is missing now. We had 144 and now we have 143. And we had 90 protons and now we have 91. So of all 144 of these neutrons, 143 of them didn't do anything. The net change is this. That's the net change, which takes us full circle back to the beginning, which is what I told you a neutron does when it decays. So beta decay is actually a neutron decay within the nucleus. And we can go even deeper, and we will. What's happening to a neutron to do this? There's something going on inside of a neutron. And it's more complicated than saying there's these three particles that are just locked together. How much energy is released? I really believe you understand what we need to do here. You need to find this total energy, this total mass, and compare it to the initial mass by taking final mass minus initial mass, and then using E equals mc squared. Are you with me? That this will be, I can't highlight it, I lost my highlighter. This mass on the right will be the mass of an electron plus the mass of protactinium. What about the antineutrino? It's massless. It actually does have a little tiny mass, but it's so tiny that it doesn't affect anything. So you're going to add those together, and you will discover, and I'm exaggerating things, that mass on the right is smaller than the mass on the left, which means you've lost mass, which means you've lost energy, you've released energy. And the energy change will be equal to the change in the mass times the speed of light squared, as long as you work in kilograms. I'm going to give everybody a couple of minutes to do that. And I realize that I'm kind of forcing you maybe to be a little outside of your comfort zone by not having to write everything down, but I've tried to do that throughout the whole course. I'm going to do the calculation up here as well. And I will be yapping along the way, just in case you need some help. So the mass afterwards is 234.042759 plus 0.000549. I'm perfectly aware I do not need brackets here, but I'm indicating that that's the total mass afterwards. Double check my entries. Oh, look at that. And you might be surprised how one decimal will throw your answer way off. You'll be doing some problems today and in the coming days where you'll get an answer and it's like way off, and it's because you missed a decimal. 234.0436. Oh, no, I had it right. See, even that, you know what? I was looking at the wrong one all of a sudden. My mind and eyes drifted up to thorium. So 234.042759 plus the electron mass. I'm going to subtract the mass of the thorium that we started off with. $234.043601. By the way, before I hit equals, I don't know how much any of you have been using your textbook for help. Just steer clear of the chapters dealing with nuclear physics in your textbook, because they do things wildly different. Okay? This is what I get for the change in mass. That's atomic mass units. Before I load that in here for m minus m, I need to convert that to kilograms. That many kilograms. Not a huge change in mass. But this is only one nucleus, right? We're just talking about how much mass change and energy change for one, was it thorium-234? Yeah. That's a mass change. Now I can multiply by the speed of light squared and reveal to you that very often I will put 9 times 10 to the 16 for the speed of light squared, because 3 squared is 9 and 10 to the 8 squared is 10 to the 16. This is the energy released by one thorium-234 nucleus. Where does that energy go? It's a great question. Where does this energy go? Where does this 274 kilo electron volts of energy go? The kinetic energy of the beta particle and of the nucleus that's left over, because it will be pushed backwards. This is where this energy comes from. The kinetic energy of the alpha particle in example 1 came from the loss of mass. And that's where we stop today. We've covered alpha decay and beta decay. And if you flip ahead a couple of pages, there's a set of problems starting on the bottom or near the bottom of page 37